Yeah, g'day, it's Charlie ZL2CTM. Just wanted to do a quick update on some of the test software that I'm just using here to try and nut out the best way of first calibrating out the internal errors of the system and then running a test plot and plotting on the screen. So like I say, purely test software here. At some point in time I want to introduce be it a number keypad or the rotary encoder here to allow different selections between, say, filters, for example these filters up here, or a crystal filter, or whatever. But at the moment it's just using some test software ranging from 2 to 30 megahertz and then just plotting it. So purely just get an idea of how the software may work. 3 buttons here. The white wire is a test, so that's number 2 selection, and then the red wire is for calibration. So for example, just for interest's sake, if you were to first turn it on and try and test, the system's going to tell you that you need to calibrate first. Try to do that again, same thing, you need to calibrate first. So for calibration, at the moment the device under test has been short-circuited out, so we've got a little jumper wire here. Just to reiterate, out of the DDS is the amplifier, the 70 megahertz low pass filter, into our device under test. The output's going into the 808307, and then the output voltage on that orange wire there is feeding back into the Arduino in through the analog port. So the system's telling me that I need to calibrate, so let's do a calibration. So what the calibration is doing there, it's now just running through. That's in percentage. And if I was to draw what's happening, so we know that the output of, if I can just zoom up on that, we know that the output of the 9850 will slowly drop off, as well as the amplifier. So in an ideal world, we want to present to the device under test a standard set or constant voltage across the frequency range, so F down here. But we know that it's dropping off, so at the moment we've got a calibration array, and we'll look at the software in a sec, and we're just taking a series of readings across that frequency range. At the conclusion of running through the calibration, in other words, determining what those various points are across the range, it then doubles back, finds out what the maximum reading was, and then runs back through the array to determine what the error voltage is between the ideal maximum constant voltage and then the individual test voltages via frequency. Those error voltages there, or offsets you want to call them, whatever, are then stored in our cal array for the various frequency points. So that's the calibration array. So then when you then want to do a test, which is the white wire, we can then run away and do a test. So that's now going to test a straight piece of wire, so the expectation is we would have a straight line, which we can see there just on the top of the screen. So there's a nice straight line across there, it's not dropping off. So what it's done there is it's now done exactly the same thing using our test array, and it's run through the frequency. Let me just move that there a bit. Again from our 2 to 30 megs in this particular case, and it is taking a series of measurements, and then as it's taking its measurement, it's then adding on the error. So in this particular case, it's about right here. It's going to add on a little bit more and then store that value in the array. That one there is going to add a little bit more, and it's going to do that. So that's what it does. It basically just adds in those error voltages as it takes the test scan, and then stores that answer in the test array. It then runs around and then plots it. There is one other factor which we'll look in the software. This screen here is 480 by 320. So there is one other factor. Once it's created the test array, it'll then run through, find out what the maximum value was for any particular test run, and then it scales on that, so that when it plots on the screen itself, we want the maximum level to be at the top of the screen, and then the plot to come down from there. I want this to be 0 dB, so in other words, we've got a straight linkage there, so we want it's effectively 0 attenuation, so I want to be there at the top of the screen, which is here. And then, oopsie daisy, apologies. Down the left hand side, we've got a series of tick marks. So minus 10, 20, 30, 40, 50, 60 dB, and they're calibrated. So based on that 25 microvolts per dB, doing the conversions with the mega. So that mega analog input has 0 to 1024 divisions. And so based on that, we can work out what 10 dB, 20, or what the divisions will be for attenuation. So if I was now to remove that link and put in, say, this low pass filter, so that fits in there, and if we were to test that one again, that's our white wire. So it's now going to run through and scan that filter, and using the offset values and give us a plot. So what we can see there, this is a 80 meter low pass filter. We can start to see there. So again, the maximum or the least amount of attenuation or max gain, or the pass band, so to speak, of that particular filter want to be at the top of the screen, so 0 dB, and then from that point onwards we can see there what it looks like per frequency. Again, this is just purely test software. It's not refined in any way, shape or form, but so 20 megs, say again 2 megahertz on the left hand side, 16 megs, and then 30 megs on the right hand side. As we can see here, we're getting down to roughly minus 40 dB, and then sort of gradually climbing. So noting the issues with the local ambient RF noise here and the sensitivity of the AD9850, and also acknowledging that at the moment, purely because this is just a test setup just to play around, none of this is shielded, so we're getting down to the ambient noise floor in this particular room. So there's every expectation, although I'm hoping, that should at least this portion of the board or test setup be in a shielded box, as been suggested in some of the comments on the last video, then hopefully we can then drive that down another 20 or so dB. So that would be the expectation. But again, for the purposes of test and to sort of iron out the calibration routines, this is good enough to see what's going on. Yeah, for interest's sake, if we were to take that 40 meter one out and put in, say again, the 80 meter and put in a 40. So what we say, white was our test. So we just test that, and we'll get an idea of what that particular filter is doing. Again, we can now see that its passband extends significantly further before dropping off. Anyway, so just taking a little quick look at the code. Let me just see if we can zoom up on that. How's that looking? Might just come out a little bit there. So, nothing too spectacular here. So let me just race up to the top. I think, for interest's sake, so got a couple of arrays here. We've got a test array, which you talked about, and a calibration array. At the moment, both of those arrays are set at 500. I was initially playing around with having the arrays at 480. So in other words, one array position per pixel width of the screen. The screen is 480 by 320. I upped that to 500 because I was noticing when we first go into the test and calibration, there must be some shock or a little bit of settling required to get some good accurate figures. So I thought I'd go to 500 and then just ditch the first 20 and only start in terms of actually plotting and recording from position 20 onwards, and that's certainly cleaned up the data significantly. I won't go into every particular line here, but basically setting up the screen, setting up the DDS, the 9850, setting up the various input pins, as well as the analog pin there for reading the voltage. In terms of the analog reference here, I've elected to set the quantization level maximum in terms of the voltages to 2.56 volts, the internal V reference. I'm getting around at the moment 2 volts max coming into the Arduino, so rather than that sort of defaulting to 5, I'm sort of using 2.56 just to get a little bit more accurate levels on the analog to digital converter. The serial port there, we're just using that to do some debugging, and eventually later on with the final software using that to output test data for retention or for external plotting. I won't talk about setting up the display in that. So the main loop itself, like I say, purely test software. Got a menu switch that just displays the main menu. There's a calibration switch and a test switch. The calibration switch will run away and do the calibrate routine, and the test switch will do the test only if it's been calibrated first. So here calibrate equals 0, in other words it hasn't been calibrated, it'll tell you need to calibrate first. If it has been calibrated, this if will fail, and then it will get run through and actually do the test itself. So let's just run down to the calibrate routine first. Some local variables, just sprinting to the screen that it's actually doing some calibrating, just very quickly running through and just making sure that for each time it runs through the calibrate routine that the initial array has been zeroed, so that's what we're running through there, and here's the sort of meat and the potatoes here, so to speak. So this for loop here, let me see, it's been picked up in the screen. It's starting at the start frequency, it's going through to it equals the stop frequency, and the incrementing each time is the difference between the start and the stop divided by the array size. I thought it's a nice easy way of sort of just working out what the increments will be. So with the actual for loop itself, it's setting the frequency, it's then reading on that analog input the voltage and dumping it straight into the calibration array at point X. So it's running through from X all the way through from 0 through to 499 or 500 total. And just sort of keep the user interested in sort of what's going on, it's just dumping a percentage complete to the screen. So 100% divided by 500 divisions equals 0.2, so it just increments by 0.2 each time, and it runs through until it falls out and it's completed the frequency range. And what it's doing here now, we talked about needing to determine what the maximum level was on the cal. And this is what it's doing here. So now it's going to run through that array, but starting at position 20. So it runs through the array and it determines what is the maximum voltage that was recorded during the calibration. So as you can see here, so if the cal array at any position X is greater than the max cal voltage, then the max cal voltage becomes that point. So once it's determined that, it then runs back through the array again, and I must admit I haven't looked to see if this can be reduced in any way, but it's fast enough for me. It then runs back through the array, and for each position it replaces it with that maximum voltage that it determined in the step above minus what was in it. So I've now replaced voltages with what I've called an error offset. So that's that small little arrow. So the difference between the straight line maximum and any particular reading. So that's now what's sitting in our cal array. We now set cal to 1, so we can tell the system that you actually have calibrated, and then goes back to the main menu. So back at the main menu, again with the normal loop, if you were now to select test, cal was now set to 1, so it will allow you to actually go through and test. So now we've got our device under test. Very simple sort of setup, some local variables, it's telling you it's testing. We're just making sure that the test array is zeroized before we go in and do a process very similar to what we did with the calibration. Again, starting with this for loop here at the start frequency, running through to the stop frequency, and again incrementing by the whole range of frequencies divided by array size, which is 500. So each time it goes through, it sets the DDS to that frequency. It then populates the test array with what it's seeing on the input plus what the calibration array offset error is for that particular frequency. So now we're basically taking into consideration any inaccuracies or non-linearities we have with the test setup. And of course then it also tells you by your percentage complete. Once it's completed doing that, we need to do a bit of scaling to make sure that 0 dB, or the maximum or least amount of attenuation, is at the top of the screen. So here again it starts at position 20, so we want to dump any of the rubbish up front, and it's going to run through the array and again looking for the maximum test voltage. So exactly the same as we saw down here, down the bottom, test array X, if that's greater than what's currently stored as our max test voltage, then the max test voltage becomes that one. And once it's been through there, it then determines what the scale should be. So the max test voltage divided by our screen height, or 320 pixels, gives us our scale. We can then run back through the array and apply the scale. So for any array, test array X, so in other words we're starting at the very beginning, and that array position becomes that array position divided by scale, if that makes sense. I don't think I explained that very well, but essentially just running back through the array and applying the scale to each array position. I had to put here cal equals 1 again because I was getting an error where for whatever reason this was causing cal, when it was a Boolean statement, to be like minus 2490, and then it was all over the place. It was very strange. I don't know if there's a part of memory being overwritten or what the story was, but to get around that problem I've just reassigned cal equals 1 here. If I don't do that, the next time I want to do test, it was saying you haven't calibrated. Well, I have calibrated, so this was just a way of reassigning that. So once it's been through and done our test voltages, it's scaled them, it then calls up the function to actually go and plot it. So the plot the test is very straightforward. It just starts at position number 20 in our test array. Again, just dumping all the rubbish up front. So starting at 20 and running through to the end of the array. And it's just plotting. So draw pixel x minus 20. So I've got x minus 20 there just to start the plotting at the very left-hand edge of the screen. If I didn't do that, because x is starting at 20 here, it would have started at 20 positions in, which I didn't want. So I've offset that by taking away 20, and then 319, so that's the maximum height of the screen, minus our test array point, and that gives us where it will start to plot down. Once it's finished doing the test plot, it draws the scales. So those scale points there, our 10, 20, 30, 40, 50 dB marks, down from our 0 dB at the top of the screen. So like I say, just some quick test software. I'll probably dump that up onto the blog if people want to play with it. As we say in the aviation industry with our advisory circulars, it is a means of compliance. It is not the only means of compliance. It is certainly not the best way, but it is a way. So it seems to work quite nicely. So like I say, I think the next steps will be to probably just keep potting around, I think, with the software. Look to incorporate a user interface. I'm not quite sure what error on the side of a rotary encoder or a keypad again, and then look to build that up, and then in due course have it mounted in the box. But like I say, just wanted to do a quick video just to run through the approach I've decided to take to offset any errors in the system. It seems to work quite well, because at the end of the day, if I was to short circuit that again, run the test, which is white, we should get a straight line. So then I'm pretty confident then that any non-linearities have been taken out of the system, and there's our straight line up top. Anyway, I'll say 73's there. I'll be away for a little while, and we'll keep on playing when I get back. Cheers all.